Thank you, Aarti, for your presentation. It's my immense pleasure to introduce our first eminent speaker, Dr. Rabibrata Mukherjee, who is well known in the field of surface patterning, self-assembly, and thin film dewetting. Dr. Rabibrata Mukherjee is presently a professor at Department of Chemical Engineering at IIT Kharagpur. He obtained his PhD from IIT Kanpur in year 2007. He joined IIT Kharagpur in the Department of Chemical Engineering as an assistant professor in 2009 and became a professor in 2018. Prior to joining IIT Kharagpur, he was a scientist at CSIR, Central Glass and Ceramic Research Institute, between 1997 and 2009. He is an internationally recognized expert in soft nanopatterning and thin film instability, with specific emphasis on ordering and arranging objects by confined self-organization at nanoscale and mesoscale. So far, he has published 80 international journal papers and holds 7 Indian patents. He has also been awarded the CSIR Young Scientist Award in 2007, the MRSI Medal in 2014, and the SERB Star Award in 2020. He is presently the chairman of DST-funded Sophisticated Analytical and Technical Help Institute, SATI, at IIT Kharagpur. So without wasting any time, let's welcome Professor Rabibrata Mukherjee to enlighten us with his presentation on topic nanoparticle mediated stabilization and morphology modulation in polymer blend and bilayer thin films. I would request all the viewers to post their questions in YouTube chat box. We'll take them up at the end of this webinar.
Thank you, Ruxana, for this kind introduction, which is, you'll soon realize it makes no merit because anyway, for the reasons probably I will not share online. I must thank Chandra, and more than that, congratulate Professor Chandrasekhar Sharma for developing such a wonderful laboratory at IIT Hyderabad, which sort of coincides with roughly the 10-year celebration of IIT Hyderabad itself. The institute, needless to say, is actually scaring us, the older IITs, heavily, and it's knocking at the doors of turning out to be one of the top and premier institutes of the country. I have no doubt about that. And I would not hesitate in saying that Carbon Lab at IIT Hyderabad is probably the Kohinoor of IIT Hyderabad. And all the students who have joined us, I should thank your lucky stars and feel extremely privileged that you have a mentor like Chandra, who is not only an outstanding faculty, outstanding researcher, a very young and very dynamic achiever, but also a very, very nice human being. In fact, as you said that I had to graduate in 2007, it's more like a push from behind because otherwise Chandra would have graduated before me. So I had to somehow sum up my thesis, submit and say goodbye. Manish is a witness, so I can say all this. So with this, let me try to share my screen. And if you get disappointed with the talk, I'm sorry about it, not much I can do. Fault lies entirely with Chandra, but here we go. So what I'm going to talk in the next 25 minutes or so is on thin film instability, something I have been doing for ages, and I do nothing else, unlike Chandra, who has deviated into so many verticals. So we will look into the effect of nanoparticle in thin films. And I'm very glad to listen to the previous lecture by Aarti because more than anybody else, Chandra will appreciate that it has strong overlap with the type of work I do, hydrophobic and self-cleaning surfaces. But more importantly, since we were talking about photovoltaic devices, one such photovoltaic device, which is probably pitted as the future of photovoltaics beyond silicon technology, is the bulk heterojunction solar cells. And in fact, the type of work I'm going to talk about is of immense importance in bulk heterojunction solar cells because since the bulk heterojunction solar cells or the organic photovoltaics are indirect bandgap materials, excitons come into play there, and exciton lifetime is an important issue. Therefore, you'd like to have interfaces as closely available as possible, and that would require even distribution of the two phases. And nanoparticle containing polymer thin films are actually a good model system for understanding the phenomena or essentially the degradation of such solar cells. So the outline of my talk is I will talk to the audience a little bit about this so-called thin film instability, what exactly is so special. There might be non-experts who will get an idea. And then straight away, I will go on to what I have to present, the effect of nanoparticle addition to dewetting films and to polymer blends if time permits. So if I ask a general question, what is so special about the nanoscale? Well, probably the most common answer that I will get is the quantum confinement effect. Or in other words, if you make things very, very small, if you go down to nano length scale, essentially the band structure starts to change. And therefore, intensive properties starts to become extensive. And therefore, probably it is known to many of you that semi-crystalline quantum dots, if you can tailor their size, they sort of start emitting in different colors. For example, if you take some solution of gold nanoparticles, they don't look beautiful like gold. They look dirty brown like this because the surface plasmon resonance or the nature of the surface plasmon resonance changes, etc., etc. So this is a very, very well appreciated aspect of the so-called nanotechnology. But there is another aspect of nanotechnology which is not that well appreciated, or the nanoscience or the nanoscale, and that is this length scale is entirely dominated by van der Waals interaction or the intermolecular interactions. So it turns out that probably many of you are aware about the van der Waals interaction, what it is, the most common being the induced dipole type interaction. And the strength of this interaction scales as 1 by x to the power 6. And please remember that essentially the gravitational force or the potential energy sort of scales as mgh. So it's h to the power 1, and here it is h to the power minus 6. So now it's very simple mathematics that if you keep on reducing h at very low length scale, mgh tends to 0, while 1 by h to the power 6 picks up. Therefore, roughly this the strength of this induced dipole interaction stretches by roughly around 10 nanometer, which is the non-retarded van der Waals interaction, right? So it has, there is no effect of gravity, and staying even in our Earth, this is a length scale where you can almost feel everything at a microgravity situation. One can do a bit of simple mathematics and can show that the strength of this interaction, instead of the two particles, let's say molecule, stretches by around 10 nanometers and scales as 1 by x to the power 6. But between two surfaces, it becomes a little longer range, and the scaling nature of the scaling changes to 1 by d squared. So it sort of stretches, the interaction stretches by around 100 nanometer or so between two surfaces. So based on this understanding, we actually define a thin film as something. So film, everybody knows, everybody talks about coatings. We see coatings everywhere, starting from paints to those of us who are wearing spectacles. Most of the spectacles come with some coating of the other. Most of the devices we use, touchpad, they all come with some coating or the other. Now, have we asked a question, how thick are these coatings? Now, these coatings, in most cases, the present technology is also to go for optically transparent coatings, which performs the functionality. For example, when you buy a spectacle to a child, you will probably go for an anti-scratch coating. Many of us wear, in fact, Chandra used to wear this chromatic coating, so which used to turn black when he used to go out. So how thick are these coatings? So there is a physics behind it. Certainly, the coating is not what you want to have. The coating once is there to provide some functionality. So you don't want to make this coating very, very thin. But then comes the question, how thin can you go? And it turns out that there is a restriction on that. Why? Because of the so-called definition of the thin film that I'm going to present. What it means is that in our context, a film is thin if there is an active van der Waals interaction between the two interfaces. So what sort of thickness are we talking about? We just talked that between two surfaces, the van der Waals interaction stretches by about 100 nanometer. So essentially, if the film is thinner than 100 nanometer, there is an active non-zero interaction between these two interfaces. This is what is called the disjoining pressure. Now, it turns out that based on the material of the film, based on the spreading coefficient, right, this interaction can be negative or attractive or repulsive. And please do understand that if you are talking about a liquid film, the surface of a liquid film always has fluctuations because of the internal kinetic energy of the molecules. Typically, so even if you look at the surface of a bucket of water, there are these fluctuations, but these fluctuations, nothing happens. The moment there is some fluctuations, surface tension or the so-called Laplace pressure flattens it out, and that's over. But when you are now talking about an ultra-thin film, where you have these fluctuations on the surface, right? So you need to understand that there is a local variation in the film thickness, and as a consequence of that, what may happen, the strength of the disjoining pressure changes from point to point. And if the nature of the interaction between the film and the surface, or the top surface of the film and the substrate, is attractive, then the surface tension or the Laplace pressure, which was trying to stabilize the film, now actually has a competition. And based on the relative magnitude of the disjoining pressure and the Laplace pressure, these undulations may not stabilize any further, and the film can spontaneously lead to rupture. Right? So this is a situation. What you will see is actually a polystyrene film heated above its glass transition temperature to take it to a liquid state. And all you do is do nothing. And you see that the film has disintegrated into these holes, and these holes evolve and it forms some droplets. So I was asking how thin a coating you should go for. These are the restrictions. That is the reason you cannot go for very, very thin coatings, right? So you end up taking coatings which are slightly thicker. And then, for example, a simple application like a spectacle, if you see, and if you want to have 2-3 layers of coating for different functionalities, you are actually adding, to avoid or circumvent the scare of the spontaneous instability, a thickness of a coating which might be few microns, and then you might be ending up having 20 micron of material in front of your glasses. And just now we were talking about reflection and absorption. So please do understand that maybe 10% or 8% of the light that is coming gets absorbed into these layers. So there is always a demand, industrial demand, for developing ultra-thin stable coatings, which are also very important from the standpoint of microelectronic industry. Your lab is associated with MEMS activities, and therefore it is known to all of you that miniaturization is actually the key, right? So this is a physics that has been rather well investigated, but still it's a rather new research area, because the whole activity started around 1990. So it's just about 30 years of Dewetting science we are celebrating. Compared to if students are here, let's say in core chemical engineering, you study still very fancy topics like boundary layer, for example, Prandtl boundary layer. Do not forget which is in place there from 1908. So it's already a 110-year-old concept. Right now, Arti was talking about hydrophobic surfaces. So that is associated with Cassie and Wenzel's state of wetting. Please do understand that these papers were published in 1945. So that's already there for about 75 years. So compared to that, this is a relatively new area of research which is going on. So many of us, including our mentors, have made their careers out of the physics associated with this type of dewetting and how it evolves. In fact, Professor Ashutosh Sharma is internationally famous, and it's not an overstatement that this particular paper, along with Rajesh, who is now a faculty at IIT Delhi, actually is considered as a benchmark paper, where they simulated based on nonlinear simulations this morphological evolution sequence of a dewetting film, and the results could be directly compared with the experimental results. So this was in 1998. It still stands out as an outstanding benchmark paper. There have been a lot of additional activities, and there has been very high profile papers in Nature Materials as late as 2002 and 2005. The reasons for dewetting to a large extent are still unknown, because it shows, as we discussed, that the dewetting should take place only when the interaction is attractive. That means that you have a film on a non-wettable surface, but there are a large number of examples where you see dewetting even on a wettable surface. So people have started to argue probably it's the residual stresses, non-equilibrium configuration of the polymer chains during the spin coating process, and everything might be reason for dewetting. And trust me, it is not yet resolved fully. So it's obvious that from the standpoint of coating, it is bad, but it is also interesting to note that you almost do nothing and you create large number of nanostructures. And I do not need to tell to this audience that nanostructures find wide application in several areas. So only problem is a spontaneous instability mediated structure is always random and isotropic. So there has been a lot of work, even we have contributed in this area for a while, of making these films dewetted on topographically patterned substrates, and then you can align these structures either in the form of aligned droplets or undulating threads and whatnot. So all type of very fancy looking structures we could create. These structures have no utility, of course, let me add as a sort of a deterrent, but nonetheless, the physics is very, very rich. We could create a beautiful alternate droplet array with two polymers, which is very fancy, very difficult to create, very delicate control and understanding of the science that is going on. This particular work by Nandini led to the almost not a discovery, but almost identification of a new phenomena called spin dewetting, where you see dewetting during spin coating itself. And then we realized that many times when a beginner tries to do spin coating and says that a good film has not come, and you attribute your cleaning was not good and this and that, you throw it away. It's not exactly that. There is a very, very interesting physics where the evaporation dynamics of the solvent and the Marangoni flow, everything coupled together with the non-wettability of the surface on a rotating platform, which might lead to the rupture of the casting solution during spin coating itself. So all these things we have done, and we could create some beautiful structures with orders, more organized structures with bilayers. Everything is there. So anybody interested can look into our older papers. But bottom line is, this is bad. this is bad means dewetting is undesirable from the standpoint of coating industry. So there has been a lot of activity in suppressing this type of dewetting. One of the things is to functionalize the surface, modify the polymers, cross-link them, etc., which are all difficult to scale. So one beautiful technique that Manisha's former boss, Alamgir Karim, and his group came up with way back in 2000, again, another absolutely stunning and almost a topic-defining paper, I would say, is to add nanoparticles. They added, the first work was done with fullerene, in trace amount to a dewetting film, and they could show that a film which would otherwise dewet above a critical concentration of the nanoparticles, and which is very, very less, like 1% or something like that, weight by weight, the film becomes completely stable. I would like the audience to take note of a particular word, above a critical concentration. Above a critical concentration of the nanoparticles, the film becomes stable. So there has been several aspects. So once something comes up, a lot of people start exploring in derivative problems and start identifying the mechanism that is going on. And please do understand that a stabilization problem does not remain a microscopic problem anymore, because under a microscope, you take a film and you see nothing happens. So what conclusion do you do? Of course, you say that I have stabilized the film, which is great, which might be very, very useful from the standpoint of coating, but then you need to dig out the science, why it is stabilizing, etc., etc. So you have to start relying on spectroscopic technique and other techniques as well. So even we did some work with this. In fact, this was my last work at IIT Kanpur before I left with Satinder, another good friend of all of us, where we could show that we could take some particles which do not preferentially phase segregate, and there is some sort of a virtual cross-linking around these particles within the polymer matrix, and there is a rheology mediated stabilization also. This is not the most common mechanism. There can be other mechanisms. And Manish will remember that was the time when we had our micro Raman installed. So this was a very fancy measurement that Satinder did for me, where we could, based on this micro Raman signal embedded on the atomic force microscope, can pick up or localize or identify the localization of the particles around growing holes. So this is not I'm going to talk about. This is already a 10-year-old work. So the main reason which is considered for the stabilization of these films is that it is argued, it's largely an argument, largely a speculation, that these particles actually migrate to the free surface. And why does the particles migrate to the free surface during annealing? Because of the fact it might be enthalpic, or the thermodynamics might be based on the surface energy of the particle, the polymer, the surface, but more importantly, the entropic contributions come into play. Why? Because a polymer chain that is attached to the free surface or at the substrate surface of the film. So this is the substrate, and here you have the film. So a polymer chain that is attached to the substrate actually has reduced conformational entropy, because the polymer chain cannot sort of oscillate in all directions because you have a rigid substrate in one side. So if a particle now migrates to the substrate, fills up a spot and releases one polymer chain, which migrates back to the bulk, then the polymer chain gains conformational entropy. So there is always a competition and balance between the enthalpic effect and the entropic effect. And the physics is absolutely fascinating. Beautiful physics is there. So we also looked into this again in collaboration with Karim, Karim's group. One of my students, Sudeshna, spent about 3 months there in Akron. Karim was then at Akron. And so we looked into these dewetting phenomena on surfaces with particle containing films, on surfaces with different surface energy. And we showed that there is actually a non-trivial contribution of the surface energy also, which at times can actually override the entropic effects. So all these we studied, but still at that point of time, we were heavily limited to atomic force microscopy and microscopy-based techniques only, because that is a background that sort of I have inherited. But more and more, we were starting to realize that if we need to identify what exactly is the role of these particles, we need to probably probe a little deeper. So anyway, so again, here the take-home message is the films showed complete stabilization after or above a critical nanoparticle concentration, right? So if this much is clear, maybe I will do a quick sum up before I start showing the newer results. So we actually understand that you have a thin film, you can have a thin film which on a non-wettable surface is prone to spontaneous dewetting, but you can add some nanoparticles or filler particles of various sorts. You can take gold nanoparticles, you can take fullerene nanoparticles, you can take graphene sheets, RGO sheets, you can take other type of customized quantum dot particles. If you add them, So generic phenomena is same. This instability can be suppressed above a critical concentration of the nanoparticles. Also, for a polymer film, how do you trigger the dewetting? The polymer film typically used as a model system for such studies, it's a hydrodynamic instability. So all the evolution takes place in the liquid phase. But you do not work with a regular liquid like water or hexane because of the fact that this type of liquid will evaporate, right? And therefore you will not know what is the phenomena due to disjoining pressure and what is happening because of evaporation. And also you cannot do solid state characterization later like scanning electron microscopy or atomic force microscopy. So a beautiful technique is to take a polymer film, heat it above its glass transition temperature, to take it to the liquid form where it undergoes all the morphological evolution, and then simply cool it down, quench it. So not only you can wait till the end and see what is the final consequence, go all the way up to droplet, but just the way as we play a movie here and can pause at any time and say this is an intermediate, you can do that also in real life, right? So here are some more details I will skip. So here is something I'd like to highlight. However, for such films, the dewetting can also be triggered by exposing these films to solvent vapor. That's another very, very standard route. So what happens when you expose it to or keep such a film in a solvent vapor chamber, the solvent molecule starts penetrating into the film, right? Because this is a good solvent for your polymer. So the film swells, and it is believed that the viscosity reduces because of the solvent penetration. Probably there is a little bit of swelling. And as a consequence, the glass transition temperature drops below the room temperature and the film eventually evolves. The community, unfortunately or fortunately or whatever, have used this solvent vapor induced dewetting and this thermal dewetting almost as an interchangeable technique. So you want to do a dewetting experiment, you just either do thermal annealing or you do solvent vapor annealing. You rarely care about what you are doing. And you do some calculation of the length scale and you plot and you show that it's resembling the spinodal dewetting or whatever, and everybody had been very happy about it. So one question as we were trying to look into this problem, we asked is it really, are the techniques same or there is some difference? So whatever the community knew was, yeah, in solvent vapor annealing mediated dewetting, there is a bit of swelling. So the actual film that is dewetting is probably a little thicker, and that's why you get a little larger droplets or larger features. And you see very fast dewetting as compared to thermal dewetting. Then the general belief was that, yeah, probably because the solvent molecules are penetrating, there is a significant drop in the viscosity, and that is probably playing this effect. The other major keyword was, in all this nanoparticle induced stabilization I mentioned, the films all got stable after a critical nanoparticle concentration. And people have concentrated only on that. So nobody till date had looked carefully into what happens in terms of the morphology and the length scale, as well as the dynamics of this nanoparticle, very less amount of nanoparticle containing films which still dewett. So these are the two problems we collectively looked into. And the first set of results we have is that we have films of the same thickness. You can see 12, 20, 38, and 55. Remember, we are all experimentalists out here. And in experiment, you don't have any do loop. So you have to painstakingly make these films, do them, and you have to do some bit of design of experiment, what type of thickness to take, etc., etc. It's not like a simulation where you would like to see the result from 1 nanometer to 1000 nanometer, just run a program which will run for 50 days or 15 days or 5 days or 15 hours or whatever. So the first observation that we had was, if in thermal annealing, a 55 nanometer thick film was not even dewetting. And the other films were dewetting, but the timeline, look at the timeline. So a 12 nanometer thick film was taking 4 hours. 20 nanometer thick film was taking 4.5 hours. This one, 38 nanometer thick film was taking close to 20 days, yeah, some 15 days or something like that. So it's very slow dynamics. And it is understandable, after all, these are heated polymer melt. So polymer melt, long chain, entanglement is there, low viscosity. So the dynamics is very, very slow, understandable. In contrast, you do solvent vapor exposure. So it's half minute, 5 minutes, 6 minutes, 16 minutes, and you can dewett a film all the way up to 55 nanometer. That's what we checked. We could have gone up to 80 nanometer, 90 nanometer. There is no end to it. We limited our investigation up to this range. And the same old belief, well, solvent molecules are penetrating, the viscosity. And see, as chemical engineers, we are all trained in such a way, or Manish is a physicist, we are all trained in such a way that whenever you see for a fluidic system, the dynamics is very, very fast, you are tend to believe the viscosity is very, very less, right? This is the standard belief we have. And polymer is a non-Newtonian fluid, etc., etc. We know all of that. So this is what the community knew. We plotted some of these usual variation of the periodicity, droplet diameter, time of dewetting, and this is very interesting. You can see that the times, there is an orders difference. So solvent vapor induced dewetting time was of the order of minute to 10 minutes. Instead, in thermal annealing, it was like order of days. So anyway, we sort of thought that we have discovered nothing new. We just quantified it. And then we looked into some little bit more critical measurements. So one thing we measured, again, in the literature, we did not find any measurement. Typically, this type of measurement should be done or can be done in a neutron, but we did not have an access to a neutron. Either we had saturated polymer. So we did a very clever ellipsometric measurement, and for the first time, we could come up with some numbers. So you see, when you do a solvent vapor exposure, it's almost a 75% swelling across the board in all cases, or 50% swelling across the board in all cases that you see based on the thickness. So from that, you can also calculate the solvent uptake. Then we decided that let us calculate some numbers critically. Instead of always being quantitative, let's try to quantify what we are observing. So first thing we did was we calculated the glass transition temperature from what is known as the Fleury-Fox equation. And that showed that upon solvent vapor, the glass transition temperature of polystyrene drops to -80°C instead of 110°C. So yes, the conjecture people have that at room temperature, you have a liquid-like film is indeed valid. Then we calculated from the Martin's equation, the melt viscosity of the solvent vapor exposed polymer, polystyrene. And this is the equation. So while working on this, particularly the rebuttal of this paper, we actually learned a lot of stuff. We learned about the Huggins constant and Martin equation, etc., etc. And here came the real surprise for us. From the literature, you can see that at 105°C or just above the glass transition, so sorry, this is not 105, this is 150, I guess. Yeah, right. So TG is 105, so this is around 150. The temperature at which we did the thermal annealing of the films, the melt viscosity is 2.2 into 10 to the power 7 Pascal second, which is great. And upon calculation, we found that the solvent vapor annealed samples, the melt viscosity is 9.8 into 10 to the power 6 Pascal second. It's completely contrary to the general belief we had that solvent vapor exposed films have a drastic drop in viscosity. In fact, it is very close, and only at 170°C instead of 150°C, if you hit the film at 170°C thermal annealing, the viscosities match identically. We did that as control experiments also, and we saw that for the thermally annealed sample, the timeline was very, very long, even at 170°C. So the first thing that we realized is reduction of viscosity is not responsible for this ultra-fast dynamics. So then we started to look into more certain additional issues. One of them is in solvent vapor exposure, what happens? What happens is ultimately the solvent molecules are penetrating through the film. So it's a process of diffusion. So from the Fick's second law, Anuja did some calculations and we came up that the time, roughly order of time for the solvent molecules, so the concentration of the solvent molecules to maximize at the interface is the film thickness squared divided by 2D. And we took from the literature or calculated the value of D. And based on that, we saw that the type of films we are looking at based on their thickness variation, the TM varies between 0.3 to 6.3 seconds. And you are talking about even in solvent vapor dewetting, timeline of dewetting to be of the order of minutes. So as soon as you start your experiment, almost in no time the solvent vapor reaches the substrate, right? So this is what was happening. So once we realized that the solvent vapor was reaching the substrate, then there was a question. So what happens once the solvent molecules reaches the substrate? Does it spread over the substrate on its own, or doesn't it? Or what remains, or what happens? So then we figured out there is a concept of replacement spreading coefficient, which actually looks into the spreading coefficient of the present polymer versus if the polymer is replaced with the solvent. And we figured out that if we have a replacement spreading coefficient as a value greater than as a positive value, then it indicates that the solvent will actually spread on the substrate. And in fact, it turns out if you calculate, the SREP is positive. So now the picture became very clear. So what was happening is in solvent vapor annealing, the solvent molecule was actually flooding the substrate. And the dewetting or the rupture, what you were seeing on the substrate, is of the solvent, and therefore it was so fast. And the polymer molecule was just sort of floating on top of these, in a dissolved condition, on a top of this solvent layer. And it was just following the contours of the solvent molecule, right? So with that, we could explain the fast dynamics as well as the rapid dynamics. Then we did some more experiments with this nanoparticle containing dewetting, right? So we did some thermal annealing. Of course, the timelines were completely different. For example, this image, for 5% nanoparticle, 1,000 minutes, and 5% nanoparticle solvent vapor is 1.2 minutes. But now we understand, so we are no longer afraid of that. So here are some variations. Most important is the completely different timelines. And we also see how the variation of periodicity and DD. There is some nonlinear dependence, which is still to be resolved fully. Here is some dynamics of oil growth in thermal annealing. Solvent vapor dynamics was so fast we could not capture it. And we can also see that in thermal annealing, these are the effect of the film thickness. So 55 nanometer, if you do a thermal annealing, it almost does not dewet. And 55 nanometer, if you do a solvent vapor annealing, so it dewets pretty well. So again, the statement that nanoparticle-induced addition of nanoparticles stabilizes a film needs to be relooked. It's a question of what triggering mechanism or dewetting engendering mechanism you are adopting that also needs to be employed. So something maybe if you say that, well, all films above 40 nanometer are stable if the nanoparticle concentration is just 0.05%, it also needs to come with a tag that if you do a thermal annealing, the same film is going to be unstable if you do a solvent vapor annealing. So these are very important findings that came out from this paper. And however, the most important slide is probably this one, again, where we did some very careful atomic force microscopy, actually to see what happens to the nanoparticles. Because here, please do remember, we could not do an X-ray scattering because the film was dewetting, and you don't have a continuous film. So because of the correlated roughness you have, you will not get some fringes, right? So, so what we did was, we did some very careful atomic force microscopy, and we saw that the particles, actually, you can see in the atomic force microscope image that the particles agglomerate on the top of the surface of a dewetted drop when you do a thermal annealing as crowns. In contrast, since the solvent has gone all the way down to the substrate, a dewetted drop through solvent vapor annealing is completely pristine on the top. And below, when you remove the particles very carefully, we have a protocol for doing that, you see that the substrate has signatures of these particles. In contrast, if you have a continuous film, what you see that there is a signature of some particles at the top interface as well as at the bottom interface, and collectively they stabilize the film. So this was one major learning we had. I am running out of time, so here are the conclusions of the AFM images. Most important thing is particle containing film dewetting, and if you do the thermal annealing, the particles go on the top of the surface. Solvent vapor annealing, the particles go to the bottom of the substrate. This is one of the very fascinating and delicate observations. So this is a mint fresh result. I mean, it's yet to get a page number, so it's just published out there, and I thought I would share it today. And Chandra, that is the reason I had to prepare a new lecture. Therefore, nothing was prepared till last evening. So I'm running out of time, but I will just take 2 more minutes to showcase one more interesting result. And this is related to polymer blend, something Manish knows very well. So if you mix 2 polymers and just cast them from a common solvent, you directly get some phase separated morphology. It's because of the fact that 2 polymers, let's say if they're symmetric 50-50, both of them do not occupy 50% of the space. There will be difference in their solubility, there will be difference in their affinity, there will be difference in their molecular weight. And because of variety of reasons, one phase will occupy more than its designated amount. Right? Let's say 150% phase will occupy 60% of the surface. Therefore, the remaining 50% will be cramped into 40%. And you straight away see some self-organized morphology right after spin coating. You never get a flat film, actually. So there has been a lot of research on this area, on the mechanism, how it happens. And the most well-established mechanism, based on some in situ dynamic light scattering measurement, which was published in Nature Materials, says that there is actually an in situ bilayer formation, and which undergoes again a hydrodynamic instability during spin coating and leads to this type of lateral phase segregation. So in this particular work, so of course there's a lot of data out here which I will not get the time to explain, where we looked into the morphology of a polymer blend changes as a film thickness. So here you vary the film thickness as well as its composition. So here you see a blend which is 75% polystyrene, 15%, 25% PMMA. It's a 50-50 and it is 25-75. So if you now vary the film thickness, in certain cases the morphology changes, becomes larger or whatever. But in certain cases, for example, in the symmetric blend, you can see some sort of a phase reversal. So for example, up to 26 nanometer, you had a PMMA continuous domain, and at 46 nanometer, you have a PS continuous domain. And don't forget that you are actually using a silicon wafer, which always gets covered with a PMMA because of the polar bonding that is present, the carbonyl group that's present in PMMA. So now what we decided to look into how the morphology gets altered if you add nanoparticles. So you see some change in morphology, very symmetric data, systematic data. I will not go into the detail, but some results are very, very exciting. So you add some nanoparticles and you see the phase separation is almost suppressed. So if the phase separation is suppressed and you have two phases, so what exactly is happening? Either you are sort of creating a bilayer, in situ bilayer, or you are somehow arresting the spreading. So 50% phase occupies 50% only. So I'll skip all the detail. So we looked in detail into this particular sample. We did some XPS and figured out that there is signature of gold going to the surface, free surface. So probably during the spin coating itself, along with evaporation and due to the thermodynamic effects, some gold particles go to the free surface. But more interestingly, along with Professor Milan Sanyal's group at SINP and this flagship program of DST that's running on, we used the Indian beamline at Tsukuba and could figure out or find out the electron density profile along the depth of the samples. This is something absolutely revealing for a person who doesn't have a physics background like me and doesn't know spectroscopic technique or did not know the power of spectroscopic technique. So based on that, what we figured out that this sample actually undergoes a vertical phase separation. So what now happens, what was reported in the Nature Materials paper, that there is an in situ phase separation because of the instability at the interface, because of the nanoparticle, that instability gets suppressed. And now what you are doing is, in a polymer blend, by adding some nanoparticles, you are almost getting, in a one-shot process, a bilayer, which otherwise you would have required to coat following two sequential spin coating techniques. So that sort of makes it, and if it can be scalable to dip coating or something like that, it can be an absolutely fascinating technique for creating multi-layer coatings in one go. And we have all the details. So this is also reasonably recent work. If somebody is interested, you can look into it. So I reached the conclusion. So we presented some glimpse of our activities on nanoparticle containing films and polymer blends. And we now have a very precise understanding on the different mechanisms of solvent vapor induced dewetting versus thermal dewetting, where the particles go, how it affects the morphology of a blend. In fact, these works actually give rise to more questions than they answer. And these are model systems. I work on very simple problems, gold nanoparticle, PS, PMMA, no use, no translational value. But let me remind that particularly this polymer blend work with nanoparticles is actually very, very closely related to the whole physics of bulk heterojunction solar cells. And that understanding is not there. We still struggle primarily because of the fact that they are unable to control the phase separation and the dynamics subsequently during deployment. So the presence of the particle significantly alters the morphology. So I must thank my students at Kharagpur, and today I particularly presented the work done by Anuja, who took a long time but did some outstanding work and is about to finish her PhD. And Sudeshna and particularly Nandini did the initial work on pattern-directed dewetting. The collaborations with Professor Milan Sanyal's group at Saha Institute of Nuclear Physics, now he's at SNMO Center, and an honorary professor at Nonlinear Center. Dr. Orko De, it's Mr. He is a PhD now, he will beat me, he sees this. And my former colleague from CGCRI, Dr. Gautam De, who helped us in the XPS measurements. I must also thank my mentor, Professor Ashutosh Sharma, all our mentors actually, speaker and the host, and funding from the travel to Indian Beamline by Department of Science and Technology, and an internal in-house challenge grant project that I have, which is funded from IIT Kharagpur. And the reason I was invited was this, Chandra, Sai Baba hairstyle at that point of time. 2008, Chandra was learning how to make CD patterns, and it did help you. You and Manish got a ACS AMI, if I remember correctly, based on the learnings that I imparted, and you never acknowledged me in that paper. So these are some old photographs I dug out. We had some real wonderful time. Chandra was much younger to be, but my immediate junior. And that's the beauty of Ashutosh Sharma's lab, I would say, that despite all of us being scattered all over the country, and Sir, now the topmost scientist of the country in terms of he's essentially the custodian of Indian science, the bonding remains. And it's great to see that each one of us are I am the least one out of the whole lot, are doing excellent work, and Chandra being one of the flagship ones along with Dipankar and a few others. Manish is shaping up the Nanoscience Center at IIT Kanpur very, very nicely. A beautiful national facility out here. And so with that, and remembering some of the beautiful memories we had, Chandra, it's time for me to say thank you, and I will stop here. This is another picture where you see the host as well as both the speaker for today. It's a 14-year-old picture now. Time flies. Thank you very much for your attention.
Thank you so much, Dr. Rabibrata Mukherjee, for such an interesting and insightful talk. Again, I would request...
Found it interesting.
Yeah, it's about dewetting, sir. We get more somewhat idea about dewetting and all. Yeah. Again, I would request all the viewers to post their questions in the YouTube chat box. We will take them up at the end of this webinar. Moving to the next speaker for today's webinar, we now look forward to Dr. Manisham Kulkarni's talk. Dr. Manisham Kulkarni is a Senior Scientific Officer at Center for Nanosciences, IIT Kanpur.